First of all, we would like to thank you for coming after lunch. We know this can be a tricky slot, or siesta will become, but we'll try to make it entertaining. There is a demo part, and the software part is pre-recorded, so there'll be no problem here. We didn't come here alone, Arnau and myself. This is our program for today. We will tell you what's a hacking token. Who wasn't here last year, we will explain the concept, the hardware and software concept, and how we've materialized this. But we're not here alone, but we come with more people, a couple of associations, the University of Barcelona, and I want to take this opportunity to introduce us. For whoever doesn't know us, this is our first RootedCON. I am Arnau, I am 20 years old, and I study mathematics and computer engineering at the University of Barcelona, and I participated in several security conferences in the last 3-4 years, and the association I represent here is Hacking Jury, which is new from the end of 2016. We devote ourselves to social issues and security, computer security. We've organized workshops about things like Internet of Things, etc. I come from an association called Physitronica. Was founded many years ago, a few freakies who like to play with these tools, and then some of us moved on to electronics as well and did the 2 degrees, and computer security is where at the university is where I got in touch with this topic, and we met in that environment, and we wanted to do something together. And last year we heard this wonderful talk given by Hugo, Sweet Tools of Mine, where he explained many things. He talked about different topics, but the main thread was about hacking tools. He talked about software a lot, and he presented we went to pay and he showed a few slides about hacking tokens, and he defined them as a device with a single goal, which is to compromise with a combination of software and hardware, and to have something that was accessible with very little, something that was footprint and discrete and autonomous stuff. And we started looking for candidates where we thought we could pick up a daily object, or with a power feeding, and something that is not noticeable, and that we could sort of give a present to. And from the part of electronic engineering, having thought about it for a while, we thought about battery chargers and drones or thermostats, whatever. But in the end, our conclusion was to try it out with a power bank, because it's becoming quite ubiquitous, because people tend to get one of those at home, so the victim will actually manage the electronic the powering of the device. And we felt that it made a reference to, it was one of the few things that had not been realized yet, and in that sense, why not to do it without including. If you tell somebody, I give you as a present the power bank, and then we can do things with that. So I'm going to show you a few slides about the hardware part. I'll do a short demo, and then we will move on to the software that Arnau will tell you about it. So what do we want to do? We want to reverse a power bank. We have to go down and if you take a power bank that you have at home that doesn't work, and this doesn't load anymore, and you open it up, because some of them are not so easy to open, this is what you'll find. This is a very simple one with a single cell, a LiPo cell. For this type of batteries, like in mobile phones. And you find this little circuit here, which has several parts. As explained in this slide, there's a lot of electronics, but if you want to simplify it from this type of battery, if you start from the right, this type of batteries are batteries that do not have a constant sort of downloading in terms of voltage. Well, none of them are constant in that sense, but in this case that's particularly serious, and they can go from 3.6 to 4.2 volts, although nominally they're always in 3.7. And this is a mess, because the problem of these batteries is not that, but the fact that in order to load them up and to prevent them from exploding, you have to load them with the same discharging curve with a special controller so that it is charged at the same tension. And that's how you explain this loading circuit, and the protection circuit is to prevent over discharging when we're discharging the battery. And what the protection circuit does is to separate the of the battery when those things come up. This bad circuit is not simple. We could spend hours in power electronics, but you can have to accept that it picks up any tension below 5, and it takes us to 5 volts. You have 2 amperes that depend on the input level, with a bit of loss, but it allows us to charge the mobile phone, which is what they do. This is a detailed list of components. I'm not going to go into detail, but you can look at it afterwards. To pick up the components, to go to Google and look in more detail, you can do so. And a question before we go into it, fully into it, the software people are they're going to say, I want to have a Wi-Fi here, what can we do? And the big question is, we're going to have a microcontroller, and we're going to need a Wi-Fi output or something of the sort. So the state of the art, there are plenty of things. I guess you'll be familiar with some of these cards and the whole ecosystem. I've included a variety. As you can see, Texas Instruments, an American company that has a lot of material and cards that are very, very reasonably priced. And in the end, we decided to stay with something quite standard, which is an Arduino with its microcontroller. And we do that in development card. This is a Arduino Micro Leonardo or Explora. And it's a 32U4 and the another MCU V3 ESP8266, and we've chosen Arduino because it's present in different places. It can work with 5 volts and 3.3 volts and logic, and it implements in a native way the USB stack, which is in that sense is different and better than many microchips, where you have to implement USB translators, a serial USB translator, so that you can program it and to access it. That's something that we can discuss. And the node MCUV3, we've chosen it because it's becoming famous. It's quite well known because it has Wi-Fi aerial embedded, and it gives us that access that we would need. In this sense, this is not a single solution. You can find solutions in the internet where they implement partial solutions, for instance, to take an SP and put a very small LiPo battery to do some attacks or exercises of a few hours in power band, or you can find another partial solution, which is to take the SP and connect it to the Leonardo Arduino, and the diagram is a solution like any other one, and we've chosen this one because it can go to 3.3, so we can go from 3.6 to 3.3, but the Arduino will charge at 5 volts, so we'll try to put it in parallel post, in parallel to any mobile or any other charging device. There's a reason for this. We can also have a sensor in the battery to get more information about what's going on. And this is a simplified scheme, although it's only looking at the charging source. This is also a very simplified circuit of how the data are going and how the communication is happening, and we can use both the micro USB of the power bank and to get information and connect to the microcontrollers, and we could also eventually do a communication between them, I to C type, for instance. So I'm going to move on to the hardware.
So in this regard, I'm just going to devote about 10 minutes to make sure that everything makes sense, to show that we can actually charge a mobile device or do different things. I don't know whether you can hear it, see it well here. And if you deassemble a power bank, you find this. Here's a circuit I was talking about earlier. There isn't much more to say really. And here is the battery. The battery is a commercial battery. It can be found on the market. And here we have a similar battery, including some charging protection circuits. So we bought a few of these batteries and we began to do a demo. Another thing you need to acquire is a circuit. They're separate. Okay. So here you can see this, and if you have hardware doubts, let us know. This is designed for the power bank, and these can be acquired separately into parts. The micro USB with the charging circuit and the battery protection at the back. This is one of the components that have been listed earlier. You may also acquire the step-up, the discharging circuit, which is very small here. You have the coil, the condenser, and the rest of the step-up circuit in this example of this power bank. So if you have these two components, here I'm going to do a bit of soldering, but here I've welded one of these. This one goes here, and now I just need a battery.
Por ejemplo, esta batería de aquí, no sé con el LED la luz qué tal irá, pero bueno.
I don't actually know whether the light will work, but let's have a look.
Perdonad. Vale, ahora yo creo que sí. Vale, si yo por ejemplo...
Okay, so now I think it will work, and we need to charge the battery. This is a pretty standard charger for Raspberry Pi. Can you actually see the red bit? And here's the charging circuit. It detects there's a battery, it charges it, and with the red LED it shows that it's charging. If you disconnect it, you should see the blue LED, and you can still see the red one. The red one is still on. It shows a different status, which means that I don't find the battery. So if the battery was fully charged, I would see the blue one. This is something that we know that is common, and now we want to see this charge circuit. As you may see here, there is a red LED. It's on, so you're actually getting power from the battery, those 3.6 or 3.7 volts, and getting there. if I take out the micro USB connector straight to the power, the circuit still discharges the battery, so we have a power bank. And let's see whether I can fit everything here. As you know, the USB has 4 dimensions, and this is now charging. So we're actually charging our mobile phone from the battery. This is a usual power bank. The question is, can we do this replacing this USB input by whatever we want? Let's check. So here we have the USB. And this board model, this MCU model, has 2 interesting things. We recommend this model in particular because it has 2 diodes. I don't know whether you can see them here. But these 2 small components are 2 security diodes that allow us to connect a battery at the same time with the USB directly for it to load, so that nothing burns. Right now the battery is charging, and is charging at the same time, so that the MCU node is on. In fact, if we went to the mobile demo now, I'm going to look for the former configuration. Okay. So you should have connected a SAP AP. If you want to connect, the password is the one that we had in the Arduino's example. But if we go to the navigator, to the browser, and we load this website, it says we're connected to the SP and that it's working. So now we have the proof of concept that it really works to place a ESP in the middle of a power bank. And we can start doing things. And if at home you want to work on it, you can set up a more sophisticated board, looking like a broadband. And we've started the design of the PCB, but we've had limited time. So here's the hardware part. Later we'll recover this after the part of the attacks, and now we'll talk about software. So regarding software, the first thing that we need to wonder is, so we've set all this up, we've got a device that has power, that is portable, that has Wi-Fi, that has a microcontroller. And to tackle this, which are the basic needs that we have? And here we're thinking about 4 essential bits, which are to be able to reprogram this hardware, obviously, because if it was just for one program out, the fun would be lost. We can store data, so we want to retrieve data that should be able to be stored. In turn, we want to be able to recover this data, not just that they stay in local, but that we have access to them. And it will also be interesting, just like Ismael showed the modular design of the hardware, the software should be as modular and plug-inable as possible, without changing a big and readable block. We should be able to put our bases there. So here we get to a general idea of a design of an attack with a device that has a Wi-Fi connection, and this is an abstract machine. We have the idle state, the main loop. We have the different attacks as well that you can see up there, that are like own states. They could be plugins, not depending from the rest. And in turn, we have another status that deals with recovering and storing that data. We have the abstract date of the final machine. We make it more particular right here, which is the basic proof of concept. So we have the idle state. And as you may see here, the loop has two parts. We have a microcontroller. So the loop would change between a initial status, which is to scan Wi-Fi, which is kind of random, and communicating with microcontroller to eventually be able to do things with it and talk to it. We'll see what it's for later. And then we implemented a captive portal attack, and then we have another status that deals with capturing that data. So let's talk about the loop status, which is Wi-Fi scan. As I've just mentioned, that loop status is random. It could be always at an access point mode. So the token we designed is a power bank that may be moved and may have access to different Wi-Fi networks that it may scan. So it made much more sense to be able to scan Wi-Fi in its loop instead of doing a token with a router or something fixed. And scanning Wi-Fi there would make sense because we would always have the same thing. So it was more interesting to have this. Here we have the power bank, which you can move around. So scanning with Wi-Fi here gives us much more information. And we have a few basic things. Here the token needs to act as a Wi-Fi client. It needs to scan. It scans the available Wi-Fi's in the change and keeps the name, the MAC, and the signal. We have more fields that we could store, but we think these are enough for the proofs of concept we've done. And to store this data, I don't know whether you've worked with the SSPs. You might know as PIFs, which is a standard storage system used by the SPs, and these files are stored on the same flash memory as programs, but you can actually store the program without deleting the files part. So here is how it works. It's very easy to use because it's modes for files and writing are the same one as the COpenDC. They work in the same way. They have some limitations though. They have to do with the fact that we have a microcontroller that is limited. It has 80 Ks of RAM and 4 megabytes of flash. It's very limited, and that means that the file system that we can set up is also quite limited. And here's a layout of the LSP, of the flash. On this URL you may check all the documents on SPFs, and you may see there is a space for sketches. You have the OTA, the file system, the Wi-Fi configuration. Here on these links you have all this information quite well explained. So next we're going to talk about the attack of the captive portal. We've run this attack on the network of the Barcelona University with their permission. And here, unlike in the former case, the token needed to be in access point mode, simulating the support of the captive of the open Wi-Fi of the university. To do this attack, we use the SPIFs to record those HTML files to reproduce the captive portal. And you know what that is, right? Does anyone not know what a captive portal is? Well, when you go to a hotel or public Wi-Fi, they're like, okay, you need to log in to continue. So you give your email or whatever credentials, and you can continue with the connection. So one our files simulate this captive portal. How do we make it to work with a captive portal? You may make a request, and then it takes you back to the captive portal. And the browser should say, well, you need to do it well to continue. It's as transparent as possible. And that's the normal expected behavior. However, here we need a DNS server. And here there's a very simple explanation of how it works. And as we said, we configure the access point, the gateway. We defined it randomly. So we initiate the DNS server so that all requests are sent to the gateway DP. So the two handlers, you can go to the gateway DP, what you have there may be useful, And if you don't find it, if it doesn't find where to take you, you may say, okay, go to the gateway too. So here's another scheme. It says, okay, where is any given domain? And it also reply is on this IP, which is the gateway IP for our fake captive portal. And we have an advantage here for the implementation of user experience. Browsers and the main operating systems, when they detect the requests are being replied to with the same IP, they say, okay, this is a captive portal, I'm going to give you a pop-up of logging in here. They don't mind whether this is coded, they still send you the message. And this is open in certain windows. In Android, you don't go to your browser directly, you open an internal window, and it's quite transparent, you don't know really where you're browsing around. So we have that advantage. And I'd like to quickly explain how we get data out of here. And here we need the hacking token to be in client mode. And here the hacking token, in the way we've implemented it, whenever it does a loop, and the Wi-Fi scans, if it connects configured IPs, it will connect, you will send the store file, and you will empty out the log file, because it has a limited memory. To do this, we need an external server. So we have a server, and here's a few things about it. It's a very simple server based on Python with base HTTP request handler. It has a SSL certificate, so traffic is coded from the SSP to server. It has unique IDs to identify the tokens that we may have given out, as well as the credentials, which are stored securely. And to finish, this will be uploaded to the GitHub doc hacking tokens. And what we have designed to design all the software is the MIO platform, the platform IO. This is the DevOps track. So we haven't talked about Docker, but I'm sure you know it. So in platform IO, we manage much better libraries. We were able to interact with several components at the same time. Also, the debugging is done remotely. And this ecosystem is quite nice. And it has its click part, the different IDs. And here are the natives on Atom and Visual Studio, but it may also be seen in CLI and others. So please look at platform IO if you don't know it, because it's quite interesting for this. And next we're going to look at the results of these attacks. The first one is to talk about the Evil Twin portal. This is a fake captive portal attack on the University of Barcelona, and it's able to capture those credentials that have been set to initiate the session on this captive portal. So we haven't stored the real user data and the passwords, even though the university gave us permission to do tests, but we didn't think this was appropriate. And passwords are not stored in a raw manner.
Comentar que las demos, la idea inicial era hacerlas.
Our aim is to do these live, but the organization told us, well, try not to do it live or connect an access point to the internet, because some things have happened. So if you're curious to make sure that it really works, we can show it to you later. But a bit of offset is not bad, actually. So here we have the Wi-Fi. It's detected an access point. It asks us to do the login. Put our username, and this is the captive portal there, literally. We have opened a page which is connectivity check, not just tatic.com. It says, okay, the password failed. So most internet networks for universities fail, so this is not a surprise. 1/4 of the times you connect, they don't work. So you kind of play with that bonus. So this will be stored on the SP, will be sent to the server. Okay, kind of lost the zoom, but here we are again. So what it just stores in JSON format is the username, and the password is just kept as a pattern node of what has been entered. Here are the changes in the status machine, and here we have the small JSON format that is sent out to the server with timestamps. That could be useful to do backtracking and get the hours and other things. And then the second result is okay, so we have an animal that has power, it's autonomous, it gets Wi-Fi, it stores them, sends them out to our server. So what can we do with this? So we can actually geolocate. We can do geolocation for our victim directly with the Wi-Fi data that have been collected.
No hay que
Google has an API to do this directly. We just got the data about the name, the MAC and the power, or the intensity of the signal, and that's enough. And you're going to see some examples of routes that we have been able to track. Let's see the video first. So we have a video first. So you're going to see how we have data on the server. These are real logging. These are timestamped logging with all the items. We have geolocation things regarding the Wi-Fi status. So this file has been transferred locally. Yeah, you could store it in a little server. And here we have a little script in Python that checks the Google API. And here we can generate maps. And here's a map of the taxi that goes from the Atocha central station in Madrid. And these are bars that has a straight line on Gran Via in Barcelona. And these are a couple of buses from the Barcelona University. If you remember the images, mainly the first one and this one, this is what we can geolocate by using our scanning animals. And this is a route suggested by Google Maps to go from Atocha train station to here, to Kinépolis. And you may see it here, but there is an area around here, and this big here we haven't done it. These were tunnels, by the way. So we went through a couple of tunnels where Wi-Fi was not detected. So we did a straight line from here to here. This part got crashed, but all the rest, I think this is Paseo de Extremadura, and none of this has been done. So the taxi driver got Google Maps and said, okay, I want to get here, and he took that route. And then the Barcelona map, I don't know whether you remember the shape, it went up. This point here is in University of Barcelona. We'll go up here, and we'll do a transfer, and it goes down. It's like literal. I don't know whether you've seen the video. In the University of Barcelona, there's actually a peak inside. That doesn't mean that it got us crashed, but we actually went to locker. We came back and he detected that at some point it goes up and down. Within the university, when you go to locker and come back, so it's very precise just with this. And Ismael can tell you more about it. Yeah, this is a bonus. I think we're doing well time-wise. So regarding hardware, you're like, okay, so we have a microcontroller there. We have it for battery loading or charging. And if you want to switch off the power bank, we have that microcontroller. So we began with a small microcontroller to turn off and on. I said, hey, we could have a big one, a bad USB. If my USB is open, it's quite fashionable now. And talking to them, having a reliable access point, you can actually configure them to unload Wi-Fi Barcelona, which is another captive portal. But there are many access points in Barcelona. So once the person is connected to the mobile, why shouldn't you just open a Wi-Fi point? These are ideal conditions. This obviously needs to be unblocked, but we just want you to check the information at which things happen.
Y nada, pues a bajarse los datos al servidor.
And from here you can download data to the server. It was a very small demo, a very short demo.
Vale, sí, un poquito de conclusiones para ir acabando.
So to sum up, we think we've done a great proof of concept study, quite successful. We did a test last year. I'm sure there are better solutions. In this area, and we think it's been successful. And there's feasibility in the hardware. There's hardware available in the market. It's not something esoteric. If you live in large cities such as Barcelona, Madrid, you can go to Biotronic or even to AliExpress, which is more larger stores. You can have access to the hardware. We have implemented 2 different attack vectors, and you can look at whatever you want there. So we got 2 direct attacks and 1 post-process attack. So what is the to-do list? There's some things missing. I wish I could work on the Almega to take it to 3.3 volts, but there's a whole issue of unblocking the micro. There are a few boards that have those specs, because watches may be different, clocks may be different, so most experiments are done with these items, and most official boards are 3.3, but on Fruit in China you can find non-Arduino boards with this controller that instead of 5 like the other one go at 3.3, and that will open the door to program the SP from this guy here. We also want to improve the current sensing. We have put it on an I2C sensor, and the output could also be improved. A power bank has at least 4 LEDs that indicate different things, and time-wise we couldn't do it. And regarding the tags, yes, when I showed the slide earlier, there was an area reserved for the OTA, and that's quite interesting. We've done some short tests that we can fully integrate. OTA is over the air, and here you could update things over the air, the firmware basically. You don't need physical access to that power bank to update the firmware, because we can implement another attack or do anything you want, or even change the attacks, and we can have remote access to it. So these may be done in the conditions that give you at least half of the memory available, and then you can delete all the rest. God bless hardware, and you also get half of the flash available. And these are functionality quite interesting. We've worked with it. It's not fully implemented, so that we cannot show it to you, but it's there. And we've seen projects from people who were able to put the Wi-Fi antenna in monitor mode, and they could play with it. In fact, there's a library that I want to get hold of called Exploit as ESP. I don't know whether you know it or whether you've worked with it, and I'm going to check their GitHub after this. And what else? Well, there is hardware, because right now we only have client mode USB, and the proof of concept was done to check that we could have a bad USB on a mobile device, which is not common. And the power bank is connected to the mobile device, so we don't need to connect it or force it. Well, there are, however, some devices that are kind of obsolete. So Arduino brought out a line of boards, Arduino Omega the HDK to do things with Android, with ALB. Since they have to close the ALB, those libraries are not being used, they don't work. But the chip Max 3421E allows you to have up to 4 devices on a USB host and control it from a microcontroller. And at the end of the day, the conclusion was, well, why should we have ADB if I can have a USB host? And I said, hey, BDP or MTP, give me the files. So we still need to research that. But I think they have been decatalogued. You can buy the chip, but you cannot have access to the development board, the Arduino Mega. Okay, so you can update this to add Bluetooth. If it fits, why not? That's the next update of the ESP32 with the same Wi-Fi and even more memory. Why not? And if we hadn't lost so much time yesterday, quite late, taking pictures of the power bank so you could see them well with all the devices, so we had a express photography course. And well, we have some acknowledgements and thanks to many people who have collaborated on this project. It's a project of 2 associations that we are both presenting, but with the participation of many people: Paul, Alejandro, Gerard, Enrique, Isaac, David. Many of these people are here on the front row. We'd also like to thank the University of Barcelona, as we said earlier. They subsidized part of the initial materials for the tests and gave us permissions to do these tests through the network. Eventually didn't need anything, but here we are at Rooted, and we'd like to thank Rooted for inviting us. And if you have any questions or any comments, please let us know. Here are our contact details, and please let us know if we can help. Thank you.
¿Preguntas? ¿Aquí hay alguna por aquí?
Any questions? I do have a question. A little while ago you showed a file with all the logs of the positions of the people. I guess that through Wi-Fi you don't get that data. So how do you find those positions? Excuse me, I couldn't quite hear you. You mean the positions on the spiff? Well, the geolocation that you showed. Well, there's Escape on Python. I don't know whether I have it at hand, but I can show it to you later because we have it around. And Google has a API that gives you a API key, and you can transfer JSON with data access points, with names, marks, and the power, the signal. It gives you the points and the coordinates, and then you go to Google Maps and you follow the dots. So you call the API twice, and the first call is for position and the second one for presentation. And geolocation, this triangulation, Google has done the opposite process. The Google car wasn't just doing pictures on a street view, they were also getting data, and I'm sure they'll get data of all the phones that have Google Nav. So they have the triangulation process. Reversely, they know the power of the Wi-Fi antennas, and they have lots of data. Hi, good afternoon. First of all, thank you for your speech. It's been amazing. Initially, we saw that you assessed several boards, amongst them Raspberry Zero and others, Raspberry Zero. So what made you decide to use this controller? Was it the stability, the voltage, any other thing? Okay. So the ecosystem right now, since Arduino came out in all the making industry, has been getting lots of money with microcontrollers. It was a big boom. So why shouldn't we just have a API 0? Because that's ready to have different things like a Wii, graphic interfaces. No matter how you deactivate it, you could even create a Game Boy. But we want to go to the minimal bare essentials. So what does the ESP have? It's disabled. If you want to connect 10 guys there, maybe it's not the best thing. If you want to do support or 10 connections at the same time, you may need to go to the Texas ones or to others. If you want to connect one or two, fair enough. But since you are in microcontroller, this is quite important. You're not in ARM. You're working with a machine. You have your specs. You could even put it in dormant mode. If there's not much battery in the battery sensor, you go like, okay, this is getting under 3. If when the mobile phone is charging, you have the USB attack, maybe it takes about 5 minutes, but you can work with it. And all microcontrollers have sleep modes. Some of them deeper, usually tabled. I can't answer accurately, but you have different things there. And the Texas ones really work. On the power bit, some of them from Texas Instruments go at 0.9 volts. Most of them work at 1.5 in Texas Instruments, set for block, and their consumption is a lot lower. And in the university, we work a lot with the Texas Instruments ones, and they have great energy-saving modules.
What made us decide about these two micros was low resources or low cost. They were very cheap. For 2.5, 3 euros, you can find them in AliExpress, and otherwise officially with warranty. You have for 10 euros, you have one. The ENG is also very cheap. They have very low consumption, so it's a power bank that we want to last. If in an hour you run out of battery, it's about the game of minimizing the resources and maximizing attack impact and as transparent as possible. And something that we could discuss, and thanks for the question in that sense, I thought about why choosing Arduino and Leonardo, which is 32.4 rather than the 328. The development card has an Avmega 16 sub 2, or which is more powerful and less memory. So the development card or plague of the Arduino Uno, Arduino One, you have 2 microcontrollers and you can do back to USB. You only have to program the micro controller, which is not the Arduino One, which is the other one that's doing the communication. Is that done? Yeah. It's a GitLab bootloader 2, and there's a guy who's actually uploaded that so that you can do it directly with an Arduino One in an afternoon where you're bored in just 1 hour. So you go around and you end up with solutions that are standard. We've looked for solutions that are there. There are people who work on this, but partially, so we've been integrating things, and it's a good practice because if you start from scratch, you could take an STM32. You could use the CC3200, the red one, which is, this can do almost what an open and URT, but you have a different commitment. A final question? First of all, thanks for the talk. It's been spectacular. I think that I wanted to say on the on monitor mode, you want to do that on the Arduino, running on the Arduino. Do you the hardware is clear. How are you doing? How about drivers? And the second question would be, remember that when you have it on monitor mode, the battery is gonna fall down, just to warn you. Yes, when we were doing research about what can we do with these, we looked at the library that, and there may be other ones around, and we decided let's use this to see. We haven't done it yet, but just to see, let's see if there are very specific points in time, because if we implement the LOTA, which we're about to do it, to define when it's executed and when not, if we want to localize when this person is at home and see if their Wi-Fi is well, when the person is at home, they will probably recharge the power point, so you can use the monitor mode. I have 2 sort of precious amps, but yes, you're right. There are limitations, no doubt. This is for a proof of concept. Yeah, it does say proof of concept. Sorry, the question not being asked on the microphone. We did that for Linux yet, and we've managed to do that for Android as well. And I don't think there's going to be a problem with these devices. Yes, for these devices there are libraries, because this is in the hardware. You can do it as a modem. Take a Linux or an API, and some people do it, and to act on the SSPs with the generic drivers that are already there, but it takes a lot longer. Okay, we have to stop here. Thanks very much, Ismael and Arnau. Thank you.